Hello, today I will discuss three numbers from the previous exercises that you asked me. Number two, in an experiment to demonstrate two sources interference of light, a beam of light is split into two beams using two slits 0.5 millimeters apart. And this will be D, 0.5 millimeters apart. These two beams are incident on a laboratory wall at a distance of 4 meters, and that will be the L, the slit to screen distance, 4 meters. The wavelength of light, lambda, is 550 nanometers. How far apart are two adjacent interference fringes that are formed on the laboratory wall? In this problem, two adjacent interference fringes means that we want to find the distance from bright to bright or from dark to dark fringes. So we want to find delta y, and delta y will be equal to lambda L over D. Lambda is 550 nanometers multiplied by 10 to the minus 9 in meter. L is 4 divided by 0.5 multiplied by 10 to the minus 3 meters. And I think the result here will be 4.4 millimeters. Before we continue discussing number 8 and number 10, I will give you the correct answers for the exercise. Please see if you have answered correctly. Number 1, A. Number 2, D. Number 3, A. 4, C. 5D. 6B. 7E. 8C. 9B. And number 10 is D. Now I will continue to discuss number 8 about diffraction grating. Number 8, a diffraction grating is used to measure the wavelength of monochromatic light, and you are given a diagram. This is the monochromatic light, and the first order maximum and the other first order maximum is they are forming an angle of 70 degrees. And given the spacing of the slits in the grating, 1 times 10 to the minus 6 meter. It is D, 1 times 10 to the minus 6 meter. The angle between the first order diffraction maxima is 70 degrees, and we want to find the wavelength of the light. Remember, for diffraction grating, we have this equation, D times the sine of theta equals n lambda. N is the order. D is the spacing of the slits, and this theta is the angle between the nth order to the central bright fringe. So in this case, if we have this the first order and this is another first order maxima, then this theta here will be 70 degrees divided by 2. It will be 35 degrees. So I can calculate lambda to be D times 10 to the minus 6 times the sine of 35 degrees divided by n is 1. So lambda will be 574 nanometers. You can calculate using calculator because this is not a special angle, the 35 degrees. For number 10, a diffraction grating experiment is set up using orange light of wavelength 600 nanometers. The grating has a slit separation of 2 micrometers, so D will be 2 times 10 to the minus 6 meters. And here we have the first order orange and the second order orange that are forming angles theta 1 and theta 2 to the central bright fringe or the 0th order. Now we want to find the angular separation, theta 2 minus theta 1. So we'll just use the equation, D times the sine of theta equals n lambda. And if we want to find theta 1, it belongs to the first order, so n is equal to 1. So the sine of theta 1 will be 1 multiplied by lambda. The lambda is 600 times 10 to the minus 9 divided by d. D is 2 times 10 to the minus 6. So I have calculated here that theta 1 here, or the sine of theta 1 is equal to 0.3, then theta 1 is equal to 17.45 degrees. And to find theta 2, we use the same equation. Yeah, d times the sine of theta 2 equals 2 times lambda. So the sine of theta 2 is equal to 2 multiplied by 600 times 10 to the minus 9 divided by the d is the same, 2 times 10 to the minus 6. So we have sine of theta 2 equals 0.6 and theta 2 will be, I have calculated, it is to be 36.87 degrees. So if you want to find theta 2 minus theta 1, it will be equal to 19.42 degrees. Or the answer in the option is B, yeah, 19.4 degrees. I think that's all. If you have any question, you can ask.